Hello, my name is Jun Lee. I was in charge of fairness part in my team. So today I'm gonna present a paper named Fairness Without Demographics through Adversarially Reweighted Learning. Please enjoy it. Recently, the problem of fairness in machine learning has emerged. For example, Compass, which is used to forecast which criminals are most likely to reoffend, Compass shows the racial bias that black offenders who are seen are almost twice as likely as white offenders to be labeled a high risk, but not actually reoffend. In addition, for various applications, bias measures were found for sensitive attributes such as race and gender. Therefore, many researchers have defined fairness in machine learning and studied debiasing techniques. However, the fairness studies conducted so far have problems. That is, most of researchers on fairness assume that they can access to protective features. However, the assumption that they can access to protective feature is not true in real world because there are privacy or legal issues. So in many cases, we cannot collect or use sensitive information to train or inference. For example, CFPB requires that creditors should comply fairness, but creditors cannot use demographic information to train it. So the authors represent the research question as how can we train a ML model to improve fairness when we do not know when we do not have access to protective features? To answer the previous question, we need to define what is fairness. Authors decide to use definition of Rawlsian Max Min Fairness, which maximizes the minimum expected utility across protected groups. There are another fairness definitions that named parity-based fairness, but authors choose Rawlsian Max Min Fairness because Rawlsian Max Min Fairness increase minority performance is more reasonable than just decrease gap among groups, which parity-based fairness aims to. So Rawlsian Max Min Fairness can be represented as first equation, which is H star is equal to argmax min U ds, where H is hypothesis and S is sensitive attributes and U is utility function and ds is demographics of sensitive attributes. And authors replace utility function into loss function for ease of training because utility function, which is, for example, AUC or accuracy, is not differentiable. So it is difficult to use in training. So to replace utility function into loss function, min and max is reverted. And bring ideas from reweighting and adversarial learning, the objective function can be defined as sum of lambda si multiply loss of the model. And training is conducted by training theta to minimize objective and training lambda to maximize objective to focus on high weight data points. So prior works reweight data points based on protected group memberships to debias the model. However, in our case, we don't know protected group membership, so we cannot reweight based on protected group membership like before. And there is similar work with this paper named GRO, which aims to debias the model without protected group demographic. And GRO set weights based on loss to focus on data points with larger errors. However, the emphasizing high-loss data points makes poor performance with noisy outliers because it can easily overfit to outliers which have high loss. So authors stick to information which is correlate with an observed protected group and more robust than loss which is used in DRO. So they first hypothesized unobserved protected groups are correlate with the observed features and class labels. And they checked it by inferring protected groups from observed features and labels. And the result is at the right table. And it showed that it is true within adult and SAC dataset. So, and they find computational identifiable region that an identifiable region of misclassified data points to utilize observed features and labels. For an explanation about computational identifiable region, let me give you an example in below figure. There are two protected groups which are classified by color, and the colors are cannot be accessed by trainer. And then the result of ERM, there is an incorrect positive class cluster close to decision boundary, which is circled by red circle, and that is computationally identifiable region. Data points in computational identifiable region have high loss, but they are not outliers. So authors think that they can improve worst group performance, a worst group which is not outliers, by improving performance of data points in CI region. From this, authors propose adversarially reweighted learning, which is an optimization approach that leverages the notion of computationally identifiable errors through an adversary to improve worst-case performance over unobserved protected groups S. In other words, they set weight lambda in objective function based on CI region. To utilize CI region information, they train classifier fpi to predict the data points, whether the data points is in CI region or not, so that they can emphasize data points in CI region. So the authors define lambda as 1 plus n multiplied sum of f pi of all data points over f pi of the data point. This lambda is designed according to following design rules. First, they try to prevent negative value because negative loss makes training unstable. And second, they try to prevent zero weight to fully utilize all the data points. And last, they try to prevent exploding gradients, so they use normalization. To train objective function, which is zero-sum game between lambda and zeta, ARR conduct min-max game between learner and adversary and train them alternatively. In detail, the learner tries to learn main classification tasks to minimize objective function. But however, the adversary tries to learn a classifier to predict CI region to maximize objective function. Then finally, learner can train the model which focus on data points which outweighs data points in CI region. For evaluation, they use following experimental settings. First, learner has structured that two-layer feed-forward network with 64 and 32 hidden units, and value is used to activation function. And adversary, here is an interesting point that they use a simple one-layer linear model to adversary because with complex model, it can be overfitted into outliers like DRO. and they compare with baselines. Uh, First baseline is uh, represent as baseline, which is standard ERM with uniform weights, and DRO is I mentioned before that which allocate more weights to larger errors. And they test on following datasets named others, which predict income, LSAC, which predict low school admission, and Compass, which predict recidivism. And detailed information is described in below table. And they evaluate methods based on following metrics. The first two metrics, AUC average and AUC macro average, shows overall performance of method, and the last two metrics, AUC mean and AUC minority, shows worst case performance among groups. As a result, ARR improved worst case performances within alert and LSAC dataset. However, there is performance degradation within Compass dataset. Authors argue that it is because protected groups in Compass dataset are not computationally identifiable, and even ground truth class labels are noisy. However, ARR performs better than GRO even within Compass dataset. And as I said before, ARR can improve performance of worst cases so that it leads to ARR improved overall performances. And comparison with inverse probability weighting, which set weight to inverse of probability, ARR outperformed than IPW with alert and LSAC, even IPW with no protective attributes. Authors say that because the ARL selectively outweigh incorrect protected groups, but IPW just reweight based on probability. And compared to group fairness approaches, experiments show that group fairness approaches can reduce gap between groups, but it does not always improve worst of groups. And there is some analysis to understand AR deeply in detail. Previously, we checked that AR works poor with Compass dataset, which has noise labels. So they test robustness of ARL within two aspects. First is representation bias, which means bias in group size, and second is label bias, which means there is incorrect labels. The results show that both DRO and ARL are robust to representation bias, but sensitive to label bias. Authors say that DRO and ARL are sensitive to label bias because they outweigh using prediction error, but they cannot distinguish whether labels are true or not. And they investigate weights from ARL is meaningful, and the results show that weights in ARL successfully reflect whether example is misclassified or not, and whether it is the data points is in class imbalance examples. In summary, authors propose adversarially reweighted learning to improve model fairness without accessing protected demographics. And ARR can improve model performance for worst-case protected groups, and ARR is more robust to noisy outliers because it focuses on data points in CI region, not to outliers. This is the end of my presentation. Thank you.